In our first lesson for Chapter 7, we're going to introduce some new vocabulary, some new concepts, and Chapter 7 is our introductory unit on energy. And energy in physics is called work, and we'll see why formally in a moment. But the most important thing that I want you to know up front in terms of language and what we're talking about is that work and energy are the same thing. So I absolutely would like you to put this into your notes. You need to think of work and energy as the same thing. And energy is joules. So those joules that you were talking about in chemistry still apply in physics. So work is going to have units of joules. Energy is joules. So work and energy, same thing. Now, why do we use the word work? Well, up here, we talk about the work done by a force. So it's going to be a force that transfers energy into an object, and that's going to be positive joule value for us when we calculate the energy that was transferred. And if it's something like friction that's slowing an object down, that's going to transfer energy away from the object, and that's going to be a negative joule that we'll end up calculating when we get to our equations and make numerical calculations. All right. Now, that's how to think about work. We're going to think about work as energy, joules, forces transfer energy. Well, then what is energy? Energy is motion, and motion is speed. So hopefully you have your highlighter pen ready to go just to highlight energy and speed. If something is moving fast, we say it has a lot of energy, and we'll be able to calculate exactly how many joules of energy it has once we get our equations. If something is moving slowly, we say, well, it has a little bit of energy, and we'll see the mass comes into play as well, but speed is much more important, and we'll see why again when we get to our equations. And this one is important because if something is stopped, no matter how massive it is, it has no energy. So no motion, no energy, and we'll see in chemistry you probably talked about the concept of absolute zero. That would be an absolute zero state when you have no energy, no motion at all. All right, as far as problem solving is concerned, one of the most important things you absolutely need to always keep in mind is this here. Energy does not have direction associated with it, ever. Okay, so it doesn't matter whether you are running downhill, uphill, or sideways. The amount of energy that this object would have will be based on its mass and its speed. We never, ever, ever put x hat, y hat, z hat, or indicate direction for energy, and you never did that in chemistry when you had equations that were endothermic and exothermic. You didn't say, oh, there were 10 joules released north. It was just 10 joules. So that part remains the same. And again, we've talked about some of the language here. So the wording that we're going to be using, energy is transferred to an object when it speeds up, and energy is transferred away from an object when it slows down. Now, we're not going to be saying endothermic and exothermic, but I just put it into the notes because you should be familiar with endothermic meaning positive joules, right? And exothermic meaning negative joules in chemistry when you had your chemical reactions. Okay, and we've talked about that forces do work, and that's why we introduced this language, work, transferring energy, and then that energy is given in a joule value. So I think it'll help us at this point if we move on to the next page and see what our formal definition for work and energy looks like. So in mechanics, we have a definition that's an equation. So it's an equality by definition. There is no theoretical proof that it has to be this, but it turns out to be very useful, and it works. So if someone were to ask you, what is work in physics? Okay, work is energy, and work is defined by F dot delta X. So we're back to dot products. So hopefully you can go back and review how to be a dot product taking machine. We take the magnitude of the first vector the magnitude of the second vector, notice I have the units here, newtons meters, times the cosine of the angle between the vectors drawn from a common origin, and that drawn from a common origin, of course, is very important. It's the cosine that will give us the positive or negative for our joule value, and we'll see that that's going to make perfect sense in terms of speeding up, slowing down, energy being transferred to the object or energy being transferred away from the object. So I have a simple example here of one force acting on an object as it moves to the right a distance 20 meters. So we have a 20 Newton force acting at an angle of 20 degrees, and this is just an example. There's no physical significance to it. And we're going to calculate what's happening in terms of energy transfer by using our definition. The work done on a mass equals F dot delta X equals plus or minus the number of joules of energy. And we can see here that it's the number of joules of energy because 1 joule equals 1 Newton meter. I'll bet your chemistry teachers never told you that, but that is true. Okay, so how is this force transferring energy? Well, some of the 20 Newton force is actually pulling the box to the right. How much of that 20 Newton force is pulling the box to the right? Well, it's the F cosine theta part of the 20 newtons that is pulling to the right. So F cosine theta, look, dot product gives us exactly what we need. It gives us the F cosine theta, and then we multiply it by the delta X, and we get positive or negative comes from the cosine of 20 is plus 0.94 times 20 times 20 gives us 375.9 Newton meters, which is joules, and it is positive, so this means energy is being transferred to the object. This object is speeding up. So if you are a dot product taking machine, you're going to take your dot products correctly. You always will calculate the correct value in joules that is being transferred. And of course, we'll talk about the applications or what we're looking at in the problem with the object speeding up or slowing down as we go forward. So you'll have some homework problems to get used to these basic definitions and language, and then we'll continue learning about energy.